Now that we have a good basis of RER, what it's measuring, what potential values could be, and why we are able to get those values, we're going to now try to apply those into how these RERs and substrates are then chosen for exercise. We'll look at two examples. The first example we'll see here is looking at exercise intensity. So working our way up from doing very little, maybe resting, to walking, to jogging, to running, to all-out maximal effort exercise. And in the next slide, we'll also look at duration. So giving you a set output. So telling you, say, oh, maybe cycle at 10 or 100 watts and keep doing that for a sustained amount of time, and what happens to substrates then. So again, first let's focus here on exercise intensity and how we look at what the substrates are. So first I've left some blanks here, but we can just kind of add these in. So these are 20, 40, 60, 80, and 100. I'm just going to add in the first and second there for speed's sake. But essentially, again, that idea that we're working up of exercise intensity at different percentages of our VO2 max. So 20%, something very, very easy, a very light jog. 50% of our VO2 max, a pretty good workout, and 100% all-out maximal effort. As we then look at the graph, what we're going to do is we're going to look at percent of energy coming from both carbohydrates and fats. And I've labeled the y-axis here, about 10% here at the bottom to 90% at the top. So ultimately we can look, and for example in this very first part of the graph at 20% of your exercise, you can say that the majority of substrate in which we're using, of course, would be fat and a very small amount of carbohydrates. So actually, if we were to put a number on this, if we were to give a reasonable estimate of RER, what number could that be? Hopefully you can already answer that, but the idea is when we think about this, remember our range has to be from 0.7 to 1, with the idea that 0.7 is mostly fat, 1 is mostly carb, and so we can say then a reasonable value for RER here of almost all fat and very little carbs. Maybe we would say, let's say 0.72 would be a very reasonable value to say almost all fat, very little carbs. On the opposite end of the spectrum, what we can see is at 100% of our max exercise intensity, we can see that almost all energy is being produced from carbohydrates, very little from fat. So again, we can think of what's a reasonable value for carbohydrates and fat, and this RER then would equal to, we'll say, roughly 0.97 or so, give or take. Again, these don't have to be perfect, but I do expect you to at least give me a reasonable value, something that's close. Again, in the first scenario, mostly fats, so give me a number close to 0.7. At the end, mostly carbs, almost all, so give me a number close to 1 as we work through this. And so this graph, not only does it allow us to tell us what's going on at the beginning of and the end of exercise, but we can also kind of get an idea and a pattern that emerges as we progress at different exercise intensities. So what we can see here is as we increase intensity, so from 20 to 40 to 60 to 80% of our VO2 max, we can see that the harder you exercise, the less amount of fat you burn as a substrate, and the more amount of carbohydrates that you burn. Ultimately, we see this ratio start to both decline on fats, increase on carbohydrates, and ultimately we intersect here at this position. What this intersection is it's called the crossover. Grab a pen. So this is what's known as the crossover of substrate utilization. And what this is the point in which carbohydrates are about 50%, fats are about 50% or relatively equal, and therefore we could say that a reasonable or exact, in this case, RER would be 0.85. Again, that tells us 50% carbs, 50% fats, right in the middle then of our range between 0.7 and 1, and perfectly in the middle. Oftentimes in exercise physiologists, it's often taught that this crossover is roughly 50% of your VO2 max. And it gives us a nice little principle or rule that we can use for undergrads to kind of help them remember that at approximately 50% of your VO2 max, we use 50% carbs, 50% fats, and it's also then called the 50-50-50 rule, and is kind of an easy way to remember this. Again, that 50-50-50 rule says at 50% of VO2 max, we use roughly 50% carbs, 50% fats. As we'll see in the lab, this isn't a perfect scenario. We don't always cross over or start using carbs and fats at exact equal amounts at 50%, but it's good enough to kind of remember and lock this into your brain to give you an idea. So then as we move forward, of course, we can now kind of fill in this perfect ideas. We start to use more and more carbs, less and less fats. And so what we can imagine then is RER, low intensity is 0.7, and we slowly work our way in this graph until we have an RER near 1 or almost all carbohydrates. So as we think about this, I like to pose the kind of question of what's at least the physiology and the understanding of why would our body want to use carbs at high intensities? Why not use fats? This ultimately goes back to the efficiency issues. So carbohydrates are more efficient at ATP produced at high intensities. So you should remember specifically carbs are 5.05 kcal per liter of oxygen. Whereas fats are only 4.7. I'm just going to use parentheses here to tell you that that's exactly the same. So 4.7 kcal for fat, and carbs are 5.05. So again, it makes sense is that as we start to work at higher intensities, we start to kind of say, okay, oxygen now is starting to becoming a limiting factor. We need to get every amount of ATP possible out of each carbohydrate that we can, we need to get the maximal amount of ATP out of each molecule of oxygen that we have to consume in aerobic metabolism in order to get the most out of that molecule. And so the best way to do that, of course, is then to use our carbohydrates and use less fat. So again, to kind of specifically answer this question, we would say our body uses carbs at high intensity because they are more efficient. And what we mean by more efficient is that they produce more energy per liter of oxygen than fats do. One more time. Our body uses carbs at high intensities because they are more efficient. And that means they produce more ATP per liter of oxygen than fats do. There's lots of reasons and mechanisms that we'll get to in lecture of how this exactly works, but that's at least a general principle here is that they are more efficient and we can get more ATP out of them. So we can look at our other relationship that we discussed, which is, of course, if we give an exercise intensity and we just maintain that. So here you can see I've labeled this as exercising at about 50% of VO2 max. If you're curious, we can say, what makes me say that? Well, here, if we look over here, we can see what's a reasonable RER for these values here. We're slightly more fat than carbs. So again, if we think of 0.85, it being 50-50, more carbs mean we're going to get closer to 1. So maybe we can say just a reasonable value of 0.87 or so, give or take. Again, I could do the math and we could kind of figure this out, but for this class, not necessary. I'm just trying to get a rough estimate based on the graph as we kind of look at it. More carbs than fats, so slightly closer to 1 as we move forward. But again, since they're roughly equal, we could say maybe that 50-50-50 rule comes into play here and at least gives us a rough estimate as we work. If we look at exercise duration here, again, the idea is that we're going to say, okay, exercise at this given intensity for a long duration. So in this case, we have a couple hours of exercise, and what happens to our RER. We can look at again our percent energy from carbs and fats. What we see here now is that carbohydrate usage goes down. Note, it doesn't really become very, very low percentage, kind of like the the previous graph, but nonetheless, we reduce our utilization of carbs and therefore increase the amount of fat that we're burning as duration increases. So during long duration events, right, our values become this way and get closer and closer to 0.7. And again, I could do the math to get specific, but we're just going to roughly estimate, you know, an RER here of 0.74 or so. Again, just a rough estimate. The idea is that we're going to move closer to that 0.7 value as we work our way here and use less and less carbs. So similar to our previous question, we say, well, why does our body use fats at low intensities? What's the physiology, and does it make sense in order to kind of have that transition from carbs to mostly fats in these scenarios? The primary reason, again, the reason that we highlighted earlier in class, is because we have a limited storage of carbohydrates and a massive storage of fats. So hundreds of thousands of, potentially hundreds of thousands of calories stored as fat in our body, and only 2,000 stored as carbohydrates. So therefore, during these prolonged bouts of exercise, we spare carbohydrates by using more fats, which we have plenty of. Again, we use fats at low intensity in order to spare our carbohydrate storage and utilize our fat storage, which we have a very large amount of. So hopefully by now you've got an idea of both duration and intensity on exercise. Now what we'll just say is, let's do some quick practice questions. So here's 6 examples, and what you should ultimately be able to do is be able to quickly write down what's a reasonable RER for each scenario. I'll take a break, I'll pause the video, want you to take just a few minutes to do the same, try to answer these, and then I'll give you some values that I think would work well here. Again, my goal is for you guys as students to be able to give me what I term reasonable values. So give me something that's roughly close. It doesn't have to be perfect, just that explains that you understand the content and where RER should be going. So these 6 give us kind of a good working scale on how to work through this. So first we can say, after waking up. In this scenario, most people haven't eaten in numerous hours. Right? And so their carbohydrate storages are relatively low, or we're considered in the fasted state. And so what we actually then use is most people are using more fats than they are carbs. Right? So after waking up, our RER typically is closer to 0.7, or we'll say 0.75 in this scenario, because we're lower on liver glycogen, and therefore we must use fats instead. Typically, as Americans, we then eat a breakfast. They're typically sugary, and we break our fast, hence why it's known as breakfast. And we eat something like a totally unhealthy, and I wouldn't recommend this for my exercise phys students, but provides the example of a really sugary cereal for breakfast. So in this case, as we mentioned, the body is incredible at being able to switch which substrates we use. So when we eat a sugary breakfast, maybe we then start using a lot of sugar. So we'll say just 0.93 or so here. As we move into some more of the exercise physiology, we can say at the start of exercise, roughly 50% of VO2 max. Again, we can say that 50-50-50 rule tells us that this would be about 0.85. After running for 45 minutes, this idea is that as the duration increases with no change in intensity, right, we start to utilize more fats and less carbs. So this 0.85 number that we had before should decrease and get closer to 0.7. So we'll just put it at 0.75. If we say running at maximal effort, again, this should be a 1. That tells us that we're going to use almost all carbohydrates and very little fats. And then walking at 2 miles an hour, low intensity tells us that we're going to use heavily on the carbs. heavily on the fats, less on the carbs. So we'll say an RER of about 0.72. So hopefully, if you worked through these, you get roughly these same numbers and give you a good idea of what I expect you guys to be able to do on future questions in the class.